Okay, right, so am I live yet? I can't tell. Oh, yeah. So the previous circuit that I built, the previous circuit that I designed and built, this is a new one, and I'll explain why. Right, so I started to build this new circuit, this previous circuit, and I ended up with two opto isolators, um, basically one, two, three transistors, four transistors, and the DN25, which is a MOSFET, and two LEDs. One LED didn't do a damn thing because I'd overlooked something about the DN25C, which was it requires a negative pulse to turn it off. And I was sending positive pulses to turn it off, which didn't work, obviously. Anyway, I'm going to be using all components. I'll reuse these components at some point. I'll just pull them out. But, so, you see, the problem I have is that the circuit that would trigger the pulse coil, which is going to be the coils that are on the back or underneath, which drive which get the thing started, and I'll make sure I'm not muted. No, I'm not. Otherwise, I'll be talking to myself and I'll get really angry with myself. Now, a lot of people would say, "Oh, why don't you just use an opto isolator? Put a disc on the side and a timing thing on it." Yeah, that just adds more stuff, more drag, more extra components. That's just adding more components to this instead of adding more components to a circuit board. And also, then you have to have timing holes. You have to start playing around with that. I prefer to use the coils. I explain why. The coils themselves are the actual coils that are going to be used to drive the circuit and also to do the timing, because the coils are where they are and they are in the right place. And when you put a timing disc on there, you've got to start messing about with that and trying to line it up and everything else. And there's also the other factor of using reed switches. Okay, you could use a reed switch but to trigger the circuit, but the problem with those reed switches is lifetime. They wear out. They don't last very long. They're designed for burglar alarms. They're designed so that when you open the window, it triggers an alarm. They're not designed for thousands of operations of use over a long period of time. And a lot of people who bought these reed switches found out they've got to replace them at some point because they just wear out. They just have fatigue. They have metal fatigue. They break down. I want to use solid state. Now, so I was working on my new circuit. Actually, I need to print this out. This new one I'm working on. Turn my printer on because I'm in the middle of drawing it out right now. Let me just zoom out. I've just added a bunch more components on the circuit at the moment, and print. I'm going to print it to a PDF. And that way I can orientate it more easily. Right, so I'm going to print this, and I want to set it, I want it to be landscape, so it's bigger. Just a minute. Fine, right. Right, that won't take long. Now, I'll explain what the problem was. I'm using I'll look at the old diagram first. This is the diagram actually at the moment that we're working on. Basically, I've added some bits over here, but we've got two sides to this trigger coils, right? We have a plus volts trigger, and the plus volts trigger basically goes through this trimmer, which you set the threshold point to when you want to trigger the on state, and this latches at this MOSFET will stay in a latched position, so it will stay on during the duration until we want to turn it off again. And that's another thing you can't do with reed switches. You can't time it properly because the reed switch is only triggered while the magnet's directly over it, and then it flips off again. You can't do the timing in between because I want to have the full duration. Oh, where's my other piece of paper gone? My other diagram. I'll try and explain it better if I get the other sheet. Let's just have a look. Right, okay, here we go. I've got my my rotor assembly. Now I'll explain this a little bit easier if I just show you this. I've got it upside down. Right, so this coil over here will be the trigger on state. Now, as this, let's just say these magnets have just passed the top dead center point where it's triggered on, and you get maximum amount of torque in a pulse motor circuit when the actual coil that's been energized is between the repelling magnets and the attraction magnets. Now that's what we're doing. We're actually using the coil in between the 2 points so that it's actually repelling on these magnets and it's attracting on these magnets. Now because of that we get more torque, and it's all equilibrium as well with the circuit on the coil, so the load factors are kind of equalized because it's actually pushing and pulling at the same time. And as this magnet here approaches this other coil, which is normally my exit coil, because I use these as exit coils as well as my trigger coils, which makes sense. So as this coil enters this coil here, it basically triggers the circuit off, so this magnet turns off. So this coil here, the orange thing, or red thing, whatever, this turns it on, this turns it off, but this is turned on by these magnets, and this one sends an off pulse by these magnets. So the polarity of the magnets is, well, it'll actually be the same because these magnets are actually different poles, so this might be south, this might be north. So anyway, the problem was that when we're using this as a passive circuit in here, we weren't getting enough voltage coming through here. There's basically, even without that trimmer there wasn't enough voltage at virtually standstill to operate the DN2540. There was not enough voltage because we're passing through all this network. We're passing through this Zener diode is just a clamp. It keeps the voltage on there from going too high, so it doesn't actually take effect until the voltage gets above the Zener diode voltage, which is 4.7 plus the voltage drop across the other diode. So that's a Zener down there, and since it's AC, we have two Zeners back to back or head to head, whichever. So one is forward bias, the other is reverse bias. Right. Well, because the voltage at this coming through here, and because we're passing it through a diode rectification as well, we've got a 0.7 volt drop there. We were effectively not, it wouldn't work, it wouldn't turn this on. And I did some tests yesterday. This thing didn't start working until we got to 1600 rpm, or was it almost 2000 rpm. Well, that's no good. You can't start the thing, you can't get the thing started. So I've been working on how can we have a soft starter circuit, add a soft starter circuit. Now I'll just print the new one out. Now I haven't finished it yet, so bear with me. Now this is partly right, but there's a problem here because this is basically going to be pulled down. It's basically a dead short across here, so that transistor PNP is going to be on all the time. So we really don't want it to be on all the time. We want it to be pulsed. So I've got to make some changes to this end where we've got to this end where we've got this capacitor, and which will operate more effectively with AC. Now on the breadboard I've been experimenting. This capacitor basically, when it charges up, it disables the soft starter. So the soft starter only works in the initial process of starting everything going. Once it starts to accelerate, the more it accelerates, the more it drives the soft starter, and as a soft starter accelerates and the assembly runs faster and faster and faster, this capacitor gets charged up more and more and more, and eventually the capacitor tapers off. The other circuit, which is this circuit, takes over, and this then does all the work. But we only want the soft starter to work momentarily. And I've just hooked this up to test it, just to see if I could start this by hand. And guess what? We can. So if I just took the belt off my generator, we've got the trigger coils connected to this board, to this capacitor network. Now the LED will, the red LED will actually start flashing, which means it's working. But obviously I've got no circuit hooked up to drive this thing, so it's not going to accelerate and start running because I haven't got that part of the circuit connected. So there's no this MOSFET driver here, this circuit here, is not connected to anything, so it's not going to drive it. So I'm literally just moving this by hand to test if I can get enough voltage to trigger this LED, and if I can trigger the LED, that means I can trigger my MOSFET driver. Anyway, let's see what happens when I spin it. Look at that, it's working. So I can spin it by hand to get started, but look what happens, it fades away. That's exactly what I wanted, but it's slowing down. Normally this would be accelerating, and the faster it goes, the brighter that LED would get, and then it would start to fade away. But it does work. So if we wait a few seconds, it'll discharge, the capacitors will discharge again, and then I'll be able to soft start again. So I don't know if I can do that while I'm holding the camera, but let me try and get it on. All on. Let me try and get everything on camera here, the LED and the thingy. Right, that capacitor should have discharged a bit now. Let's try again. There you go, look. And as you can see, it fades away. So yes, the soft starter will work using this configuration. So that's great news. That is really, really, really good news. So I've been playing around with it to try and get to make sure I can get this to basically work just by turning it by hand. Because let's face it, I'm not going to be able to turn this and spin this by hand at 1000 RPM. I just need something to get it started, get the ball rolling. And if the capacitor's charged up and I don't start it, that's fine. I'll just wait a few seconds for the capacitors to discharge again. Then it's another go. So yeah, mind you, the lights are on so that you can't really see it very well, but it's going to work anyway. I've just been playing around, and that's good news. So I had to breadboard this because the last time I built it, I had some issues with the soft starter not working at all, or disabled. The soft starter wasn't being disabled. Well, this time I think I'm going to sort it out anyway, because I've been doing these breadboard tests. So I wait a few seconds, it's discharged now, and normally this would be running faster and faster, and as it gets faster and faster, it's generating more voltage. It compensates for the fact that these capacitors are discharging, and it would basically take the main circuit would then take charge. The main circuit would then run it, and the soft starter would become automatically disabled simply by the fact that the capacitors here will be charged in a DC manner, and it's just simply two capacitors back to back across the AC output from that coil. Let's try it again. I'm just going to spin it slower this time. That's slower. Right. If I turn it backwards, I don't know if that will do anything. No, it doesn't make no difference. So I've got to wait for the capacitor to discharge. Let's turn the lights out. A minute. And then we're about to see it a bit better because the lights tend to be a little bit bright. It is daylight outside actually, but so alright, I'm just going to give it a few seconds to fully discharge. That's just the light reflecting on top of the can. It's nothing lit. Right, so soft starter, if we want to get this circuit built, I want it to automatically start. Well, not automatically, but I want to be able to give it a nudge, which is basically what I'm doing. Give it a quick nudge. Let's do it now. Look at that, it works. Obviously the strobing effect of the camera and everything, it's not going to show up properly, but it fades away, which is what I wanted, because by now it would have been accelerating. And yeah, also I think there's another factor. This capacitor here, this big one here, I think it needs to be discharged, because I think oh yeah, there was power in that. It wanted that was partially charged. Oh, everything's falling off. Ooh, wrong one. Is that the wrong one? Oh, maybe not. Well, the LED came on, you see, and shouldn't come on. Oh, the capacitor's are equalised, and that's what it is. I just discharged it. What fell down? Anyway, I just. Oh, magnets have grabbed me. Ah, grabbed me tin. Get off. Get off. Right. Right. So I'm being attacked by magnets. Okay. So let's just run it again. Anyway, it's still lightly dipped with it. Whoa! Look at that. Yeah, I think we're going to be fine. Oops, I'll just press some up. What do I press? Interesting. Yeah. Okay. Lights back on, I think. Okay. So that's what I'm doing at the moment. I'm just working out the best soft start circuit. I want it to focus. I'm just trying to work out the best soft start circuit to use. And I'm playing around with that at the moment. But the new diagram I just printed, I realised that there's going to be this is going to be constantly low, so I need to have basically centre tapped capacitors across this trigger coil for the for this to work properly. Otherwise, it's going to be yeah, it's not going to work properly. But we'll sort that out anyway. Right. What else is there to cover? Oh yeah, there was a problem with this board. They got from China. It's designed to high voltage or something, but it wasn't working properly. I had it running on my oscilloscope, so I tagged a little resistor on there, a 1 meg, where R3 is. It's a surface mount thing, but I don't use surface mount, so I tagged a 1 meg resistor. I think it's no, is it 1 meg or is it 15k? I can't remember now. Didn't focus when I get too close. I can't remember now. I think it's. I need a light on it. I think it was 15k or 150k or something. Can't read it. Too small. Anyway, I fixed that. I sorted that out so it would work. Focus. Right. So I fixed that. That's working now. And I had both my oscilloscopes running yesterday. One oscilloscope on my generator project, and the other oscilloscope was hooked up to this thing to test this MOSFET. And yeah, I finally got it sussed out. What else is there to mention about? Oh yeah, I had some problems with the Chinese clips. I had to the white sheath that's on the clip, it shrunk for some reason. I don't know if it's because it's been getting hot, but it's not supposed to be heat shrinked sleeving, I don't suppose, but it is shrinking, and it was causing the clips not to close properly. They were literally being held open, and they wouldn't clip on my wires. They kept falling off. I thought, what the hell's wrong with this clip? And I pulled this back and it was working fine. I thought, huh, what the hell? Then I realised it was this thing that was too tight. So yeah, if you're buying these leads from China and these things happen to, if your clips get hot at all, it just ruins this sheath, and then you have to pull the damn sheath off, which is a pain in the ass. So I'm going to find some heat shrink sleeving replace that's on there, or something, or a hood, and it's basically a plastic hood that goes on the end. I don't know what happened to it, but it's just crap. I'm gonna have to get some new leads. These just no good. These are. So anyway, that's where we are at the moment. Well, I don't know what else to say right now, but I've been testing out the DN2540, which is in here, and I got that working really well. It's working really well and very simplified. I don't actually have the Zener diodes like I showed in the diagram to clamp it, because I don't need to clamp it, because I'm not driving it very fast. I'm just spinning it, not too fast anyway. I have had the main motor running it, but yeah, it hasn't really gone to the point where it's generated too high a voltage anyway, so I might not even need the clamping the Zeners. But it's a good idea to put them in just in case, because if you do go too high in voltage, the voltage is as you get higher and higher, it can cause some issues with the circuit locking on or staying latched or something. So by clamping the voltage at certain volts, say 4.7 volts or 5 volts, keeping it a stable voltage, it means there's less adjustment on a trimmer on the gain trigger points. It means you have to adjust that less, because normally what happens is as it gets faster and faster, the voltages go up, you have to turn the trimmer down to reduce the gain. So by minimizing the fact that I have to keep adjusting the gain on a trimmer, you clamp the voltage on the input so that it doesn't go too high and it stays at an even voltage. And then when you set the trimmer pot, it's trimmed ideally no matter what speed it's running at. That's the whole point of using a clamp. It just helps to prevent problems like that. Anyway, that's it for now. At least we know that this works. Let's just spin it one more time for luck. Yay!